What do you do? So one is not a it's the feel good. Feel good. So that's a sales pitch. Now we start getting into the technical end, right? So starting off with this lecture, we'll follow it up with a small tutorial more on the laboratory evaluation of rheology. Uh, then we'll have a small quiz test over the public, right? Uh, and then after that, coffee break, followed by laboratory. So, thank you. All right. All of you ready? Okay. So, we talked about the fact that rheology or how things flow is important in 3D printing, correct? So, now we are going to look at in detail how to characterize that flow and what different parameters actually mean. Okay. All of you have squeezed a toothpaste out of a toothpaste tube, squeezed your ketchup out of the ketchup bottle, done all of those things. Right? Very similar idea. Now actually putting some math behind all that you've been involuntarily doing and understanding how those parameters actually affect what we are going to measure. So rheology is nothing but the study of flow and deformation of matter, primarily for fluids. All of those materials that you see, there's actually, if you go to YouTube, there's actually a nice play called Rheology. Also, this is this is a science play. A mother and son have done a play. They're based on physics actually, but they starts with lots of other nonsense, but it eventually ends with nice physics of rheology. I don't know why they had to do a play, but they eventually did it. So paints. When you apply paint, you see paint sagging, paints flowing, rheology, right? You see ketchup, honey, water, oil, mayonnaise, everything flows. There's actually a theory called everything flows, called pantarei in Greek. Everything flows, even mountains flow. Over geological time scales, even mountains move, right? So there's nothing that stays constant. Everything moves. In fluids, you can see that movement faster. You can measure it quicker. So flow and how liquids behave or respond to stress. Deformation is how solids behave. So if you are doing solid mechanics, you talk about deformation. Fluid mechanics, you talk about flow. Rheology, the word was coined in 1920s by Professor Bingham, in whose name there is a model, which we will see as well. It's a key to understand the flow behavior of fresh cementitious materials, which in turn influences hardened properties and durability. Remember how it comes out of the tube, how it stays in position determines how the properties are developed, correct? So again, you can also think about it in several different ways. You know, when we are young, parents say, develop your character now because that's how it's going to be behaving in the later ages. Also, same thing. You develop your character at very fresh stage, it will show up at later ages also. Fluids also does the same thing. Understanding and controlling factors affecting rheology is crucial for optimizing mixed designs. Optimizing mixed designs is very important for 3D printing. Again, like I said, it's not just about the mix design for the mix itself, but taking into consideration what also? Mix plus the printer, right? The printer and the characteristics of the printer, whether it's a ram printer, ram extrusion, screw extrusion, the printer characteristics also are important. All right, so viscosity is to liquids as elasticity is to solids. So viscosity is that fundamental property of liquids which is similar to elasticity of solids. Again, elasticity for a linear elastic material, it is a proportionality constant between stress and strain. Similarly, viscosity for a liquid is a proportionality constant between stress and not strain. Because liquids are time dependent also, we do strain rate, right? Strain as a function of time, rate of change of strain with respect to time. And then there is viscoelasticity, which is a transformation from liquids to solids. So in general rheology of cement-based materials, we look at two different types of rheological measurements, which we'll go through both. And in the laboratory also, we'll do those. One is the flow, the characteristics of the flow under a yielding regime. And then the characteristics of flow under an oscillatory regime. So oscillatory rheology and your yield rheology in a very, very generic terms. We'll see both of that. Okay, so viscosity is a resistance to flow, influences the process ability of fluids. How can you process a fluid? How much will it flow? How long can you extrude a filament? How much time do you have to extrude a filament? All of those is determined by, by viscosity, whether we can be pumping it, pouring it, all of that. So water, cake batter, molten polymer, oil, concrete, all liquids, all fluids exhibit viscosity. Can be used as a measure of energy to process the fluid. It's one of the basic rheological properties. Whether it's water, oil, honey, concrete, all of them have. Now, if you look at a viscosity scale, water, very low viscosity, coffee, a little more, oil, honey, increasing scale of viscosity, asphalt, you get to higher and higher viscosities, and difference in viscosities enable different flow behavior. Does water flow the same way as oil? Does oil flow the same way as concrete? No, right? All of those, if we want one parameter to determine or define the flow, that's going to be viscosity. Okay, and then there are Newtonian fluids and non-Newtonian fluids. We'll see that. Why is Newton coming in between here, right? He did all the elasticity, and now in fluids also is troubling us. We'll see why Newton did this also. Einstein said, you know what, if Newton can do it, I can do something in viscosity too. So there is an Einsteinian stuff too. All these scientists, there is a story. Have you heard of Hooke's law? What is Hooke's law? Stress is proportional to strain. And what is the constant of proportionality called? Young's modulus. How did Young come in between? Young was about 2 centuries after Hooke. How did Young come in between? Hooke apparently was a very paranoid scientist. Hooke was very worried that his discovery somebody will steal. So he found this spring theory, right? Elasticity. He said, as is the force, so is the deflection. So if you put a force of F, the spring deflects by delta. If you put 2F, it'll be 2 delta. So as is the force, so is the deflection. So he wrote this in Latin as ut tensio sic vis. As is the force, so is the deformation. But he did not write ut tensio sic vis. He jumbled the words and then put it somewhere. And then it took 150 years for Young to figure out that stress is proportional to strain, the same way as Hooke said, unjumbled ut tensio sic vis. So, you know what, to honor both scientists, we have Hooke's law and Young's modulus of elasticity. See, when I teach mechanics in my undergraduate class, students want to hear only this. They don't want to hear about all the other mechanics, but stories, everybody loves. So some things in between. And then Newton also was a very crazy scientist who thought that he could do no wrong, and all his theories has to be absolutely right. So he did some viscosity stories as well. All right. So low viscosity to high viscosity. A few more examples. Water is here. Mine is toothpaste. If water has a viscosity of 1, toothpaste is 80,000 times more viscous. Engine oil is about 1,000 times more viscous, just for you to give a feel of what it is. Again, if you look at viscosity, and this is again poise, water has a viscosity of 1 centipoise. 10 to the minus 3 is a poises. And then you come all the way here, mantle rocks, extremely high viscosity, which means they will also move, but very, very, very difficult to move. Remember, viscosity is a function of strain rate as well, which means something has a very, very high viscosity, which means the time scale in which they move are also very high. So time scale at which water moves, very, very small. Time scale at which concrete moves, slightly higher. Time scale at which rocks move, much, much, much higher. Is the idea clear? Basic idea of how viscosity is arranged in that continuum of water all the way to concrete. So this is elasticity, Hooke's law based on spring. So that is Hooke. Force is proportional to formation, Young's modulus as the slope. Very similarly, Newton proposed stress is linearly proportional to shear rate. Shear rate is the term that we commonly use. It is actually shear strain rate. The reason why it is shear rate is basically the velocity gradient. Velocity is distance over time. Therefore, time is already a rate here, correct? Therefore, a velocity gradient is a shear strain rate. So, shear stress and shear strain. Remember, this is now shearing. You're shearing a liquid. It's not linear flow. It is shearing. If you look at a liquid moving in the pipe, the surface of the pipe is shearing the liquid moving, correct? So, it's a shear flow that is happening. So what are Newtonian fluids? Exactly like Hookean elastic solids, Newtonian fluids are those which show a linear relationship between shear stress and shear strain rate or shear rate. Whenever you see a gamma with a dot, that's a rate. That's a shear rate. Gamma alone will be the shear strain. Correct? So what you're seeing in the y-axis is a strain rate, shear strain rate. All of you good with that? Just to make sure that the terminology is clear to all of you. So if water has so slope of that is your viscosity, obviously. So if this is the viscosity of water, honey has a higher viscosity. And fluids that demonstrate a viscosity is shown by, like solids that demonstrate elasticity is shown by a spring. I'm sure you would have seen a dashpot, correct? A damping fluid with a viscosity of eta, and eta is given as shear stress over strain rate. Good. Make sure that you have some quiz questions. You may have some quiz questions on this. I don't know. You may have them. Those kids made the quiz, so I don't know what questions are there. So if you have a liquid that is shearing across two plates, and that's probably what you will see in the lab on a parallel plate, two plates, and the liquid shearing across the two plates, one plate is constant, the other plate is moving, which means there's a gradient in velocity of the fluid that is moving with respect to the plate that is not moving, correct? That is your velocity gradient, and that velocity gradient is nothing but your shear rate. So far, good? But stop me and ask questions. Don't wait for the end of it. If you have any questions, just stop. That way. Now, the other concept is viscoelasticity. Materials that demonstrate both characteristics of a fluid and a solid, viscoelasticity. But when do they demonstrate is a question. Concrete is a viscoelastic material. Actually, asphalt is an even better example of a viscoelastic material because that demonstrates viscoelasticity very obviously at the operational rates that you see. With temperature, you will see real dependence of viscoelasticity. So what is that? So here is a very, very, very simple example, very simplified, oversimplified example if you want. So if I take a body which is at rest, and at a time A, I apply a force, an instantaneous force. I leave that force constant for a period of time. And after some time, I just take the force off. So simply take off and think of an elastic band. I take an elastic band. I'm just holding it, no force applied. At some time, I pull it. And I hold on to that elastic band for a certain amount of time. And after some time, I leave it. If the elastic band is purely elastic, it will do this, right? The function strain. So the moment I apply a force, it will have a strain. Whatever I applied, that instantaneous strain, ignore creep. Assume that I have not pulled it long enough for creep to occur. Ignore that. At that time, I have a certain elastic strain. That strain will be constant until I hold the force. Once I take the force back, it will come back to zero deformation. That's a purely elastic material. A purely viscous material, I apply a force Instantly you apply that, it is not going to get to its instantaneous strain immediately. It's taking some time. So think about honey. If I pour honey, it is not going to go and rest at its final position instantaneously. It's going to take some time flowing and getting to its final place, correct? Which means if it's a purely viscous material, its strain as a function of time will be linear, and after some time, it'll steady, it won't move again. It'll move enough unless you apply more energy, the honey will stay where it is. Correct? All of you can conceptualize that? If I take a viscoelastic material, instantly see what happens. The material thinks I am elastic. Instantly it thinks I'm elastic. It starts to behave the elastic way. Immediately some memory comes in and says, no, you're not elastic. You shouldn't be doing it. The viscous part picks up, and then that's what it is. And when you leave the force, same thing happens. Elasticity kicks in first. You have recovery of the elastic portion first, and then you will never recover your strain completely. Good. This is your viscoelastic material. So this is the idea of viscoelasticity. We will talk about viscoelasticity when we deal with oscillatory rheology, because that's also important. And then I'll explain to you those terms when we get there. So viscosity, elasticity, viscoelasticity. Everybody good with this? All right. So that's viscoelasticity. Because you have viscous and elastic portions, you will have to have a spring and a dashpot. And now, when you have a spring and dashpot, you would have seen these models. You can put it in so many different ways to mathematically explain what that is. You can have them in series. That's called a Maxwell model. You can have them in parallel. That's called a Kelvin model. Maxwell model is typically used for stress relaxation determination. Kelvin is used for creep, typically used for creep models. When you put it this way, and then you can have the equations for shear strain and shear strain rate written as a function of shear modulus and stress. Shear modulus, stress, and viscosity and time. Right? So this is basically, this is the elastic part, correct? Stress over shear modulus. That's your elastic part. And this is your viscous part, because viscosity is part of it. So that's your shear strain. And then you take the derivative of that, 1 over d gamma over dt will be that. That will be a shear strain rate. Similarly, for a Kelvin-Voigt creep model, sigma will be g gamma plus eta times gamma naught. And shear strain rate, you can always do it as a strain rate this way. Good. So again, models for viscoelasticity, things that you would have seen in some classes in the past. Okay, now rheology over time. What do cementitious materials do? So I'll give you a few, again, with some timelines of what people have thought about. 1843 is when mold cast concrete kind of started. 1931, people have defined workability. There were studies on segregation in the 50s. Rheology started to become a thing on the 50s. The grouts and slurries were developed, which relied a lot on rheology, because if you want to pump something in, if you want to spray something in, it's all the rheology of that material that's important. Flowability, pumpability, flowable, pumpable concrete became a thing in the 70s. Self-consolidating concrete picked up in the 90s. And then thixotropy, which we'll see what thixotropy is, was defined in 1970s. Extrusion-based casting, pultrusion, all of those technologies came up in the late 90s, 2000s. And then 3D printing for construction, buildability in the 2010s. So some kind of a timeline as to where this whole rheology thing has landed us at. We eventually want to come here. We are probably starting somewhere here, just to see the pattern of how we are going. Okay, how to quantify rheology? We use what's called a rheometer, which you will see in the lab in the evening session. An instrument that measures both the viscosity and the viscoelasticity of fluids, semi-solids, and solids. You get information about viscosity as a function of shear rate or stress. You can get the time and temperature dependence. Again, viscosity is time dependent, viscosity is temperature dependent too. What happens if I increase the temperature? Will the viscosity go up or come down? Viscosity comes down if you increase the temperature, right? So temperature dependence is there. We'll talk about yield stress. There are two types of yield stress. There's a static yield stress and a dynamic yield stress. We'll see what those things are. We'll talk about viscoelastic properties, where viscoelastic modulus, storage modulus, loss modulus, and the loss tangent, again with respect to time and temperature. And then you see the transient response, relaxation modulus, creep compliance, creep recovery. This pretty much is an entire semester on a rheology class. If you take a full course on rheology in a whole semester, that's pretty much what it is. Those four topics are what it is. We'll quickly condense it. We probably won't look at transient response much. We'll look at the other stuff. Rheometers. Yes, there was a question. Yes.
How we can incorporate solids? Like how can we test solids?
Depends on the torque. You have somebody manufacture a rheometer with an extremely high torque, you can test solids.
So solid is more of like elastic.
The problem is then the atomic deformations will start to manifest. Now there are equipments that you can do elastic solid rheometry. For example, if you have polymeric materials, which are solids in themselves, right? You can do rheology of polymeric materials. You can do in a dynamic mechanical analyzer, DMA. You can get relaxation modulus, creep, all of that, viscosity in a DMA. But you need an extremely high torque and you need to have sense. The problem with lots of these viscometers are that asphalt viscometer cannot be used for concrete because the torque range is different. If you are using a viscometer, a simple viscometer, you cannot use anything more than a cement paste because you don't have the torque range. At the end of the day, if you have to have enough torque to be able to twist the material, and if it's a solid, you may have to make sure that the torque that you're twisting is actually twisting the material as a whole and you're not capturing discrete atomic motions. But pretty much for lots of elastic solids, the large deformation range is not very obvious. So you really can't do that. But for polymers, it'll do a lot. Of polymers you can do in DMA. And that's why DMA you can use for polymers. You can't put in a 10-day-old cement paste and say, find my viscosity in a DMA. You will get breakage, right? You just won't measure it. All right. So these are two prominent companies that manufacture rheometers, especially for concrete. This is a company called Anton Par. This is TA Instruments. These two are the major guys that have rheometers that are commercially available. I'm sure there are lots of other companies also, but these are the leaders in the market. So basic rheometry. Now, one of the most important things to understand about rheology is that the testing is geometry dependent. Anything that you test has to be, it's dependent on the geometry. So you can have, for very low to medium viscosity, you can do concentric cylinders. So this is one cylinder and your turning cylinder is another one. And this blue stuff, I see it as blue. Some of you may see it as green. But whatever that color is that liquid in between. And you shear this cylinder in and you measure the torque required to move the liquid. So that's for concentric cylinders. You can do it for water, for oils, etc. You use a cone and plate for very low to high viscosity, parallel plate, which we use a lot for very low viscosity to soft solid. Cement paste, typically, if you have a low water cement ratio, it's like a soft solid. So that's for a parallel plate. And then for mid-modulus solids, you can do a torsion mode. Lots of the rheometers that we have for torque range in concrete won't really do the torsion mode well. You can still try torsion mode, but your system will be, you can't really even hold a cement paste in that situation. You can do polymers and torsion mode anyway. So water, again, they say water to all the way to steel, kind of a stretch to call steel. If I could call rocks, I could call steel also viscous, right? You can, at kind of, you heat steel to slightly higher temperatures, starts to yield and melt. Okay, how do rheometers work? So I talked about rotational yielding. So this is about rotational rheometry. They use angular displacement and angular strain. Like you do in your regular elastic modulus test, you do displacement control testing, right? You control the displacement, you move the machine at a preset displacement and measure the force. Similarly, rotational rheometers use angular displacements and angular strain. Why? Because it is shear, it is rotational. Anything in rotational, it has to be with an angle, correct? R theta coordinates come in, not the XYZ coordinates anymore. So if you have two plates, sliding plates, separate by a distance x, this is pulled by a force F in this direction, moves a distance of delta x, you see that this movement of delta x, whereas there is no movement in this fixed plate, so there is a velocity gradient, like I said earlier. And if you move more, the gradient becomes more. Shear stress is force divided by the area of the plate. Shear strain is delta x by your y naught, your initial distance, and shear rate is rate of that. Stress over strain is a modulus. Shear stress by shear rate is a viscosity. Very basic terms that we have seen, right? So again, in three-dimensional form, just showing this in 3 dimensions just to show what the force is. H is replaced by y. Again, y is in this direction. Now, how do they work? They are stress, strain, strain rate. This is what we want. They are all calculated signals or derived signals. The raw signals are torque, right? Your rotational force torque, angular displacement, and angular velocity. So if I'm doing a rheometer whose spindle is um, is having an angular displacement of theta, which is arc length divided by the radius, right? Angular displacement is arc length divided by radius. And then omega is the rate of change of angular displacement with time, which is your angular velocity, correct? Angular displacement with time is your angular velocity, is 1 over r ds over dt. So these are your raw signals you get. You get your angular displacement, angular velocity, and you use geometry constants. Based on what geometry you use to convert these values to shear stress, shear strain, and shear strain rate. All of this your instrument does. You really don't have to know any of this. I'm just giving you so that you know the theory and you're not using your rheometer as a black box. Your instrument and the instrument software and the instrument's calibration, the instrument manufacturer knows his geometry and his geometry constants well. He would have given you the conversion factors in the software, in your computer, in your instrument itself. You don't have to do any of those. But just to show you on the back side how things work. So viscosity and modulus calculation. Viscosity is stress over strain rate, right? Which these are the measured signals. Torque and your angular velocity, correct? And then the geometry constants for stress and strain. Again, the instrument has it depending on what your geometry is. If it's a parallel plate, it'll have one value. If it is a cup and cone, it has a different value. Or a concentric cylinder will have a different value. If a cup and cone will have a different value. So all of those are geometry constants defined by your instrument. Now, the same cup and cone from Anton Par will have a different geometry constant than the same cup and cone from TA instruments, depending on the slight change in angles of the cone, the way that the cone is machined and all of that. And that's why it's important to trust the manufacturer's numbers for all of this. And your shear modulus here is stress over strain. Again, the geometry constants for stress and strain. And then those are all the geometry constants. Geometry constants can get complicated if you want to go. You can actually go and measure. If you say that I don't like any of these geometries, I love my new geometry that I have created, no problem. Create your geometry constant and have fun. Right? You can do it. It's just that you say that that this concentric cylinder with this dimensions is not what I want. I want to change the diameter. Right? So for example, in this, if I want to change the gap displacement, you can change the gap displacement and get your new constant. But you can always do that. Um, so it's a question of how you want to do it. And you can change the radius and get a new constant. So this is how viscosity and moduli are calculated based on geometry. Now, what are the factors that affect rheology of a cement paste? I say this all the time. If somebody asks you what properties affect strength of concrete, you can never go wrong. Whatever you say will be right. Right? Everything, temperature, humidity, stress rate, my mood on that day. Your mood on the day also matters, right? Okay, if you're really angry and load the machine fast, you get a different strength. Than if you're very lazy and lethargic and load the machine slow, you get a different strength. Your mood also matters. Concrete behaves as per one of my professors once told me that when I he asked me a question and I answered something, he didn't like my answer. So he said concrete doesn't behave the way you want to behave, it behaves the way it wants to behave. So it's always true. It behaves the way it wants to behave, and therefore you will have to take care of that as well. So no answer is wrong answer here. Rheology, what does it depend? Everything that you can think of. Cement content, water cement ratio, type of cement, where did I buy the cement from, who mixed it, how fast did I mix it, what was I doing when I was mixing it. All of those factors will influence the rheology. Aggregate content, gradation, fibers. So none of those are unique, pretty much everything. But what are the factors that you think will affect rheology the most? If you are asked that question, what will you say? Give me one factor that will affect what will be the most obvious answer? Huh? Water cement ratio, like strength, same thing, right? What will affect the strength the most? What will you say? Same thing, water cement ratio. Water cement ratio is a perfectly good answer. Okay, I say, okay, water cement ratio, take it about. What will be the next thing that will affect the rheology the most? Hmm? I assume that I'm keeping everything at a constant temperature. My lab is all well controlled. What? Hmm? Aggregate to binder ratio. Forget that I have no aggregates. I have only a cement paste. Hmm? Assume that I have no admixtures. Let's make things simpler and simpler. Hmm? Type of binder. Okay. In the type of binder, what will tell me what is in the type of binder that you think will affect the most? Assume that I have no fly ash. I have only plain cement. Particle sizes, right? Assume that I have all particles of the same size. What next? When you go to a doctor and say that I'm not well, what does the doctor do? You may not know, the doctor also may not know, they are implicitly doing what? Process of elimination, right? Okay, this guy looks healthy, he may not be having this. This guy looks so, same thing, right? So if not particle size, what else? Particle shape. Shape of particles is very important. Size of particles is very important. And particle sizes, you know that, right? When you have, whether if it's aggregate or cement, or cementitious materials, you have a range of particle sizes. Rheology is a big function of the particle sizes and particle shape, or generally particle characteristics. Particle characteristics affect how particles pack in a given volume, right? Spherical particles pack very differently to angular particles. So how particles pack in a given volume will tell you how much of water is available for it to move in between the particles to shear and move the particles, which will affect the workability, which means particle size and particle shape are very influential. Because we cannot control particle size and particle shape, we happily go to an admixture guy and say, give me your magic chemical, let me add it and get my rheology correct. You can do admixtures. If you have aggregates, becomes a completely different story then. Shape of the aggregate, size of the aggregate, volume fraction of aggregates, all of those affect the rheology. With aggregates, then the paste will coat the aggregates as a coating around the aggregates. Then the paste volume thickness or paste thickness around the aggregates or total paste volume also starts to influence workability. So you can start to think about all the different kinds of things. In our discussion, we'll try to keep it simple for us to understand what the basic processes are, but make sure that all these factors are equally critical. Okay, so here is suspension rheology. What happens at particle volume fractions? At low particle volume fractions, flow is very much Newtonian, which means what is Newtonian? Stress is proportional to shear rate, and the coefficient is called viscosity, coefficient of viscosity, right? Because just remember this coefficient of viscosity, we are going to bring in a new viscosity a little later. So this is your Newton simple viscosity where stress and shear rate are proportional to each other. All right. At intermediate volume fractions, particle interactions start to occur. Oops. You'll have particle interactions starting to occur at intermediate volume fractions. You will start to shift the curve to a higher slope, viscosity increases. At even higher volume fractions, particle network happens. You will never make a cement paste like this. Nobody wants it. You will never make a cement paste like this also. Nobody wants it. You will never make a cement paste like this also. Nobody wants it. You are getting to these levels of particle volume to be really useful in cementitious systems and concrete. What happens is that there is a network of particles that form. When a network of particles form, what happens? When you have to move that fluid, the movement depends on being able to move that network, right? But once you move that network, the rest flows very easily. You see, you have to overcome a threshold to move, right? So assume that all of you are in, holding your hands with a chain, like a chain. If I need to move you, I need to apply a certain force only after which you will move. Instantly, you will not move. If it's only one person, I can start to move them instantly. You get the idea? Bad example, but you get the idea, right? So you need to start to move the network, which will require a certain stress that you need to overcome. That stress is called yield stress. You need to overcome a certain stress for this network of particles to move. If it's only one and two particles simply floating around, moving them is no big deal. As soon as I apply a stress, they're going to move. But now, as soon as I apply a stress, they're not going to move. They're waiting to get to a certain critical stress, only after which the network can. That stress is called the yield stress. Okay, that is the yield stress. And yield stress, there is shear bands and all of that. But you will see here, you see that little here. So now here, as soon as I apply a stress, it's starting to move, correct? Whereas here, as soon as I apply stress, it's starting to move. Movement requires the stress to get to a certain critical value. That critical stress is called the yield stress of the suspension. It's a big fraction of a function of solid fraction, how much of particles are there. So at very low particle volume fraction, Newtonian. See that? Some more higher, at about zero point 0.3, you start to deviate away from the Newtonian behavior. At particle volume fractions of anything more than 0.3, you tend to move away from a Newtonian behavior. Water cement ratio of 0.4, water cement ratio of zero point 0.4 is roughly equal to a volume-wise solid fraction of, water to solid, water to cement ratio of 0 0.4. A by mass is equal to about 1.26 in volume, right? That is water to solid 1.26 by volume, or 1 over 1.26 solid fraction. Get the idea? Kind of roughly. You have a marker? Oh, I got it, got it, got it. So if I have a water cement ratio of 0 0.4 by mass, that's what we always do, right? Specific gravity of cement is what? 3.15. So water cement by volume, this would be 0 0.4 times 3.15. That's roughly 1.26 or something. This is water to cement by volume of 1.26. So cement to water, or solid to liquid by volume, is 1 over 1.26. And how much is 1 over 1.26? Point, how much? 0.7-ish? whatever, 0.7, whatever it is. It's 0.7, right? It's it is somewhere. Oops. It's somewhere here in this picture. You see? Any more Newtonian? No. Oops. Sorry. It's gone way beyond Newtonian, correct? You get the idea. It's really in this extremely high non-Newtonian range. Okay? Similarly with size. So this is with volume fraction with size. Small spheres versus large spheres, viscosity as a function of shear rate. At low shear rates, small spheres will show you for the same volume fraction higher viscosity. But as you shear more and more, the size really doesn't matter. They get to the same viscosity. So viscosities are dependent on, again, just to show you the influence of size and volume fraction. Both these are two things that we are. Shape, even though cement particle shape is very important in all simulations, because we are all lazy, we'll assume all cement particles to be spherical and move on. It really doesn't make that much of a difference in your calculations, but it is a volume fraction and the size that matters. Okay, and those are shown in this picture. All of you good with this? Hmm? Where? Oh, this phi is your volume fraction. N is the number of particles. Number of particles in this simulations. 20 particles here versus 200 particles here. Because only if I increase the particles in a volume will I change the volume fraction, right? So 20 particles is 0.06, 200 particles is 0.6. So cement paste is non-Newtonian. Newtonian stress versus shear rate, straight line. Non-Newtonian, you could have convex slopes, concave slopes. You can have straight lines that are going in after a certain yield stress. All of these are non-Newtonian fluids. Right? In this, the simplest non-Newtonian fluid is what we call the ideal Bingham fluid, the guy that's here. And for some strange stroke of luck, your cement paste behaves like that. Or I'll show you it doesn't behave like that. We fooled ourselves into thinking that it behaves like that. Okay, and which is okay. That level of foolishness is okay for us. We'll live with that. We can think of this as an ideal Bingham fluid with a certain yield stress. That's your yield stress, and the slope of that is a plastic viscosity. It is not viscosity, we call it the plastic viscosity or the apparent viscosity, because viscosity is for this guy, correct? Slope of that is a viscosity. That's a slightly different term. Confused enough after lunch? Need a brain break for 5 minutes? People don't need it, looks like. They're all very active. I am feeling more sleepy than them, looks like. 5 minute break? Yeah, stretch yourselves 5 minutes and then, yeah, it's 45 minutes past the hour. So how Newtonian? So Newtonian is where shear stress is proportional to shear rate. That constant is called the viscosity, coefficient of viscosity. Non-Newtonian can be different ways, but one of the non-Newtonian that we're interested in is an ideal Bingham fluid. The reason why cement pastes are non-Newtonian is this very complex thing. Depending on who you ask and what time of the day you ask, everybody will tell you different answers. If you have admixtures, they'll say, it's non-Newtonian nature has got to do a lot with admixture cement interactions, which is true. If you put in lots of fly ash and silica fume and slag and stuff like that, that has a lot to do with the behavior. The particle concentration itself, crowding of particles in the mix itself has to do quite a bit with non-Newtonian nature. So lots of different things. Steric repulsion, hydration of cement. Cement is not going to sit in the system forever. As soon as it starts to connect with water, it's going to release ions. The solution is going to become concentrate with ions. Ionic solutions are going to start precipitating stuff depending on concentrations. That is going to change it. So lots of different reasons. So this is actually a good picture I like, because this is a very inclusive picture. Doesn't isolate, doesn't remove anything else. All the ion adsorption dissolution processes, precipitation of hydration, admixture absorption, steric hindrance, fly ash effect, everything is there. So lots of all the other defects are there. Okay. So non-Newtonian nature, just to give you a flavor for what people in the cement field use. And if you read papers, this is what you will see. So this is your Newtonian fluid, correct? Shear stress, shear rate, perfect straight line starting at the origin. This is your Bingham fluid where you need a certain yield stress to push the liquid and make it flow. But once you make it flow, it's a straight line. And that coefficient is called coefficient of plastic viscosity, whereas this we call it the coefficient of viscosity only. And instead of eta, we just invert it and write mu here. So coefficient of plastic viscosity is generally written as mu, and this shear stress that you need to start flow is called the yield stress or tau naught. And therefore, the equation for this straight line becomes y is equal to mx plus c, where c is that constant, tau naught, which is your shear stress. Good. This is your Bingham law. Now, when you increase the shear rate, when you start to mix it faster and faster, do you think the material will start to flow more or flow less? If I take a certain, if you're making, cooking a dish or something, if I stir violently, will it flow more or flow less? Generally, flow more. Such liquids which will flow more when you increase the shear rate are called shear thinning. The shear thins out or the viscosity reduces as you increase the shear rate. They're called shear thinning. Now, there are some liquids, when you cook with some sauces and all, if you put in a little bit of flour and start to mix, what happens if you start to mix more? It starts to thicken up. They are called shear thickening. So you have shear thinning fluids and shear thickening fluids, right? Shear thinning fluids are typically, and concrete typically is a shear thinning fluids, and that's why as you mix more and faster in the back of a truck, the concrete becomes more and more flowable, correct? So it's a shear thinning material, and a shear thinning material, what happens is very similar relationship. What's the difference that you notice between these two? This is linear, this is non-linear. They have, both of them have yield stresses, correct? So a yield stress fluid that behaves in a shear thinning manner, which means a non-linear relationship, which is simply written by adding a coefficient to the strain rate, nothing more. Gamma to the n. This is a model called Herschel-Buckley model. Herschel and Buckley came up with it. It's called the Herschel-Buckley model. It's a shear thinning model. So, Bingham is commonly used. Herschel-Buckley also is commonly used in cementitious metals. But I'll show you another interesting thing as we go through. So here are, how do you do steady shear measurements? You can do single shear rate steady flow. One shear rate. I'm applying a constant shear rate, making the material flow. Right? Single shear rate. I can do stepped or steady state flow. I can have a strain sweep. I can change shear rates with time and make it in a different way, which you see here. I'm making the strain shear rate change with time, correct? I can do that. Or I can do a continuous rate stress ramp. I can change it in a continuous way, not a stepped way. I can change it continuously. You can do in all different ways. Flow temperature ramp, we are not using temperature, so I'll just ignore that. So here is one common way. Now, typically, before you do the test, you have to pre-shear the material. Once you have a cement paste, you pre-shear it. Why do you pre-shear? Just to homogenize it and make sure that you have a constant starting point. Because when you do 5 different measurements, you don't want to get 5 different values. You will get 5 different values in this if you really are not careful, but you don't want that all the time. So you want to pre-shear it. You want to get to a certain shear rate. You want to quickly increase the ramp. You see that red graph here? I'm quickly increasing the shear rate in about 50 seconds to about 100 per second. Right? And then I'm holding it for some time. And then I'm dropping it back to 0. Right? And then I'm slowly increasing and coming down. So this is called the up ramp This is called the down ramp. Every point in the step that you see. So think about you walking up a flight of stairs, right? Assume that you have your heart rate monitor with you. You have your fingertip heart rate or oxygen monitor, whatever, right? So you go one step up, make a measurement. You go another step up, make a measurement. You go all the way up, you keep on taking measurements. And if you're walking up the stair, what do you think your heart rate will do? Will keep going up, right? Same thing will happen here also. As shear rates goes up, you will keep take measurements, and you take the measurements while coming down also, because viscosity measurements, yield stress measurements are very scattered. You need to have some kind of a control. Typically, some people take the up ramp value, some people take the down ramp value, some people take the average of those. Really doesn't matter. It's your choice. Be consistent with how you do it. That's all it matters. Okay, and so you can get viscosity, you can get yield stress, and provides information of when the sample is flowing. Now, there are two yield stresses I told you, static yield stress and dynamic yield stress. If I do a shear stress rate like this at a given time, what I'm getting is a dynamic yield stress. Okay, if I'm measuring shear stress as a function of time, oops, shear stress keeps on going up. And so if I'm measuring at any one time, I'm getting this plateau value, that's a dynamic modulus. But if I'm measuring it as a function of time, you will see a peak. I will show you later. That is your static yield stress. And then with strain rate, as you come down, you form a loop, a hysteresis loop. We'll see that a little later. So plastic viscosity is a measure of rate of increase in shear stress with strain. Yield stress dynamic, stress required to maintain flow once it is commenced. So this yield stress is what yield stress? Static or dynamic? Dynamic yield stress. This is the dynamic yield stress because that's a yield stress that's required to maintain the flow once the flow has started. Okay? And static yield stress is a stress required to initiate flow from rest. Dynamic yield stress, a model dependent parameter. I'll show you that as well, and attributed to a lot of different effects. So here is non-Newtonian nature. So here is what Bingham model, Kaysen model, Herschel-Buckley, different kind of models you can see here. This is shear rate as shear stress. But if I put this thing in a logarithmic form, see how the shape of the curve is changing, right? Can I now draw a straight line here? No, right? So the idea is that, and these are all called generalized Bingham models, but Bingham in 1922 came up with this model and says he has introduced this curved portion, but we conveniently ignored it. He says amount of shear, not a linear function of stress. But we assume shear to be a linear function of stress, right? In the Bingham model. This is our Bingham model. We assume linear. But Bingham himself told it is not linear. It departs at low rates of shear, peculiarly not well understood at present. In 1922, he said this is not well understood at present. In 2022, we also said, not well understood at present because Bingham said so, why bother? So we keep on using Bingham model over and over again. And the worker will do well by choosing nearly ideal condition so that the flow will be a linear function of shearing stress. We kind of do that. So every time when you do those rheology, you'll say, oh, measure from a shear rate of 5 to 100 or 10 to 100 or something to keep in that linear regime. But you never ask the question, what happens if I depart from the linear regime? Bingham said he could not measure it. The instruments in 1922 were not sophisticated. I have fabulous instruments now, why bother? So here is what you will see if you do that. Okay. So if I bring it down to much more lower yield stress, departure at low rates of shear, right? So if I bring it down to low rates of shear, which all your modern rheometers can do, come all the way down to 10 to the minus 5 rather than doing 1 to 100. So here is where 1 to 100 is what you typically use. It looks like a straight line. But what if I come down all the way, right? I get a yield stress plateau. You see this? If I measure it like this, I will simply go get my, I'll move my y-axis here and I'll say that's my yield stress, right? But no, that's not true. You actually have to go to lower stress. You get what's called the shear stress plateau. That's the apparent yields. That's called the apparent yield stress, which you don't need a model to measure. You simply will measure from the experiments itself. This is something that we have noticed it, lots of other people also have noticed such behavior. And you will see this. What does this look like for anybody who has done? Huh? What was it? Creep model, right? It is a creep model. What is creep? Same thing. Creep is exactly the same thing. Only the time scales have changed. Right? It is the same movement. Time scales have changed. That's it. Which means fundamentally the behavior is the same. Has to be the same. Now, if you, this is like a blind man seeing an elephant. If you asked him to touch the tail, have you heard the story of explaining the elephant? No? Well, five blind people were asked to explain the elephant. So one guy touched the tail and said elephant is a very rough thing. One guy touched the tusk and said elephant is a very soft thing. One guy touched the trunk and said elephant is a very long thing. Right? Depends on your perspective. But what you need is a holistic idea. If you want to do only one shear rate, you can say, yeah, Bingham is a straight line. I'll get one yield stress if I do the intercept. But if you don't want to do that, you can actually get the complete equation. Get the idea? You can get the complete equation of yield stress. So here is again, what you also see is if you fit the models, here is a Bingham model, here is a Herschel-Buckley model, here is a Kaysen model, and you look at if you come here, the actual value is in the modulus yield stress here, somewhere here, but all these values are underestimating or overestimating the yield stress, right? Now, it is not wrong if you are simply using it to compare between A, B, and C. You keep the same conditions, compare between A, B, and C, totally fine. I mean, that's what lots of fields do. But if you want absolute values, you have to be careful about how you measure it. Yeah, here apparent yield stress of 42 pascals, and you get from 63 to 24 to 45. You get all these different values. Here is 47 Pascal with limestone, and you get all those different values. So you have to understand what you need. So here is one way, the wide shear rate estimation. So here you see now, you don't have to draw a straight line here. You can go and get the apparent shear stress from a really low shear rate value. So this will be your shear stress. Don't worry about which model is the right model. Model really doesn't matter. All you need is to go down to low enough shear rates. Now, there are problems. Sometimes some machines will not be consistent, will not be stable at very low shear rates. So you do accordingly whatever you have to. But again, make sure that if you're comparing, compare between apples and apples, never compare between apples and oranges. In rheology, sometimes it's very common people will compare different numbers from different test methods, from different instrument geometries. I showed you earlier how geometries can change your values completely, but be consistent in how you measure. Rheology of fresh concrete. So if you go with Bingham, assuming that Bingham is correct for the time being, very early on, fresh state, you have a low yield stress and a low viscosity. With time, yield stress increases, viscosity increases, yield stress increases, viscosity increases as you expect with time. So the next idea, so this is rotational rheology, where you are applying a rotational or a shear stress in a parallel plate or cone or cylinder or whatever. The next one is oscillatory rheology, where now instead of applying a rotational shear, you're applying a sinusoidal impulse. Oscillatory, which means positive and negative. So apply a sinusoidal strain to a sample at a certain frequency and monitor the sample response under stress. This is again, that is your strain, that is your stress. The stress is lagging the strain by a certain angle. That is called the phase angle. The shift between input strain and input stress is called the output stress is called the phase angle. Okay, remember, strain is the input, stress is the output. Always remember that. That's why you draw strain in the x-axis and stress on the y-axis. The independent variable always in the x-axis, dependent variable in the y-axis. Strain is the independent variable, stress is the output of the dependent variable. Correct? That's how you always measure. So major difference from steady state test, your structure is preserved here. You're doing only an oscillatory strain, small oscillatory strains or oscillatory stress. You can apply stress too. When you apply all these small sinusoidal strains, you're not disturbing the material structure. Remember, in rotational rheology, you're pre-shearing everything to get to a constant rate, correct? Now you're not doing that. As is the state of the material, you're applying an oscillatory stress or strain to see how the material is responding to stress. So strain, again, because you're applying a sinusoidal strain, a strain is amplitude times sine omega t, correct? All of you have seen this in some class at some point of time, right? Gamma sine omega t. Sigma, see this here? Strain, remember viscoelastic materials. Does the material respond immediately as an impulse is applied? Remember the pictures that I showed earlier. Does it do immediately? Viscous materials, does it do immediately? It takes some time, right? Which means the strain and the stress are separated by a certain lag. And that lag, also called the phase shift, this is nothing but the difference between DC and AC. If you remember your electrical class, fundamental electrical class, difference between voltage in DC and voltage in AC, right? You have a phase angle, a lag, a phase angle that is between the input strain and the output stress. That is the phase angle delta. Therefore, stress becomes sigma naught sine omega t plus delta, right? So that is your strain, that is your stress. Now, when you apply something that is sinusoidal and when the output lags the input by a certain phase angle, you always end up in the complex regime. You cannot do real numbers anymore. You have to do complex numbers. That is why if you do AC, if you have done an electrical engineering basic class, your alternating current calculations are always in complex mode. You remember that? And if you remember that, or your AC calculations are always, your voltage is never current times resistance. There is nothing called resistance. There is something called impedance. You don't call resistance anymore, right? In AC, there is no resistance, it's impedance because you have the phase angle built into it. Therefore, you have to look at the real part and the imaginary part. Any complex number will have a real part and an imaginary part. The real part we call the storage modulus. The imaginary part we call the loss modulus. And the complex modulus, the amplitude of that is square root of sum of the squares. Right? Amplitude, like you do any complex numbers. A plus IB, and if Z is equal to A plus IB, the magnitude is A square plus B square, right? Sum of squares, square root of sum of squares. So this is your, again, the analogy is putting in a rubber ball or a tennis ball. You see here, if you put in a rubber ball, if I drop it, I'll get most of it back. I have only a little bit of loss. If it's a ball that's like a tennis ball, I'll get storage, some of the energy is lost. If I get an even more, a cork ball or a leather ball, much more is lost. Damping happens, right? So there's a lot more of loss. Same idea here. So complex modulus, complex stress over strain, written as storage modulus plus the imaginary component of that, which is the loss modulus. Stress and tan delta is the loss modulus over storage modulus, and then complex viscosity measured in oscillatory experiment. So again, this is an oscillatory. This is useful in 3D printing sometimes, and that's why I'm showing it. Not very commonly used, but sometimes it's a useful parameter to understand in 3D printing, other than just the yield stress and plastic viscosity. So oscillatory rheology, what you do is you still do a little bit of pre-shear and then stress sweep at a shear at this is called a small amplitude oscillatory shear test. Oscillatory stress or strain applied at constant frequency. Pre-shear is applied, and you find this such a curve here. So this is a shear stress sweep, sweeping from a stress of 0.01 to 1000 pascals at a very low frequency. I don't remember what the frequency is here, but what you get is your storage modulus, the red dots, the loss modulus, which is your blue dots, and as long as they are all parallel, this is your linear viscoelastic regime. Here, the material behaves in a linear viscoelastic fashion, which means your viscosity is still an acceptable term there. Linear, it is linear viscoelastic. And then the yielding happens where the values start to drop at a certain stress. You have yielding, and then once this flips the order, that's flow happens. So this is linear viscoelastic region, no flow. This is yielding, this is flow, and this stress where this really starts to flip between the complex and the loss value, or the storage of the loss values, is called your transition stress. So lots of these numbers you can determine using a oscillatory rheology experiment. So yielding zone, flow zone, um, critical stress. You can get lots of values. You have critical stress, transition stress, storage modulus, yield modulus. So all of these values sometimes are useful in characterizing rheological behavior. We'll see more of this tomorrow when we talk about extrusion as well. And then here is a strain sweep. So all of these were stress sweeps where you have stress as a function of, or storage modulus as a function of stress. You can do storage modulus as a function of strain as well as oscillatory strain, from very low 0.0001% strain to 1000% strain, and you get the same kind of behavior. So either stress sweep or strain sweep, both type of experiments are okay. Depends on what you're comfortable with, what your system is set up with. Really, in terms of values, makes no difference at all. Some people like strain sweep, some people like stress sweep. There are frequency sweep also, especially when there is temperature dependence involved. We wouldn't really worry about frequency sweep. And so that gets us to the idea of extrusion rheology, which is what we will spend time tomorrow on. So what we have looked at so far is viscosity, yield stress, both static and dynamic, the ways in which you can get yield stress for cement paste or cementitious suspension. You can get it through a Bingham model, you can get it through other models, or you can go all the way to a low shear rate and do it without any models. You can get the yield stress. You can get, that's the dynamic yield stress. You can get static yield stress. We'll see about static yield stress tomorrow, which is a time-dependent value. And there is thixotropy associated with static yield stress. That is with respect to extrusion. We'll do that tomorrow. And then with oscillatory rheology, you know that you're applying a small sinusoidal amplitude, and therefore the output stress lags the input strain by a certain angle, which causes the whole thing to be in the complex mode. Therefore, your viscoelastic parameters are complex numbers. And therefore, you have to find the magnitude of a complex number. or the ratio of the complex numbers is your loss tangent that tells you how viscous or viscoelastic the material is. You can find out the viscoelastic range, you can find the transition range, you can find the flow range, you can find the critical stress, you can find the transition stress, you can find all these different stress values which can be related to an extrusion process to understand how materials behave under extrusion better. So I told you now that earlier that not just the material, but the extrusion process also is important, right? So type of extrusion process, extrusion speed, extrusion geometry, layer height, layer width, all of those influences the material properties. Um, so there are lots of fundamental parameters in extrusion. We'll do a few things where here what we'll do is to having measured the yield stress of the suspension in the lab, which you will be seeing in a few minutes. Is there a way, because while I'm measuring the yield stress of cement paste, it is under a rotational regime. But when the extruder does the extrusion, that's not what is happening, right? I'm pushing the material through, or through a screw, my material is coming out. Where is rotation there? So it's a different kind of it. Is there a way that my extrusion yield stress can be related? Now, when it comes through, have you seen the nozzle of a 3D printer? So it is a pipe which is your bulk of your extruder plus a nozzle through which this comes out. And there is a diameter change as you go from the extruder to the nozzle. And when there is a diameter change, there is a shear stress that is involved as you change the diameter, right? That, and then there is a wall stress, there is die stress. Is there a way to do all of those? Again, people have done this. Models have been made for this for other extrusion processes. We can simply borrow from them and make slight adjustments to how that is done. Pressure drop happens across the die because you have a fluid that is flowing through a larger diameter through a smaller diameter, which means pressure increases. And as you come out from a higher pressure to an atmosphere pressure, there's a pressure drop. That pressure drop causes changes in stress and changes in flow patterns. And how does that influence it? So we'll look at some of those basic ideas of what happens. This is RAM extrusion. Even though all your 3D printing systems, whether it is a gantry printer or a robotic arm or whatever, you typically use screw extrusion, right? We'll show you that. But screw extrusion is a very complex process to model. So we simplified with a RAM extrusion with a simple piston and a die. The fundamentals are different, but you can still relate it to the processes as to how the material flows through the die entry and the die exit. And can we do some very simple tests to understand what the material is doing before we go and print. And then you see another set of curves that look exactly like the shear stress strain rate curves that you've seen in extrusion also. So all these fundamental mechanisms are somehow tied to one common ancestry. The lineage is all the same. You see all of these equations, all of these. So this is extrusion pressure versus RAM displacement. Pressure, displacement, stress, strain, same thing, right? All fundamentally the same quantities. You see that they're all related in some form or fashion, which gives us one, hope that you are in some right track, that you're doing things correctly. Two, that not all is lost. We can actually understand how these processes are happening and we don't have to be empirical all the time. Empirical actually is good. I like empirical when you know what is happening. You've repeated it 10 times. I don't want to go back and repeat the theory. I know what's happening. Empirical, great. Give me an equation. Let me go with it. But if you don't know it, being empirical sometimes will lead you to a wrong place. And that is why people who develop empirical equations this year will have to add another constant before their empirical equations next year, because now the materials change, the same equations are not holding. So what do? They put some empirical constant to fit that. The year after, the constant changes. So every year, you will have to change the constants and change it because you haven't really gotten the fundamental mechanism. What we do is, there is hope, there is a way that all of these processes are some way linked together. Let's try and find out where that is linked. That's pretty much what I have on dot. And then tomorrow we will start with extrusion rheology, more adapt. But tomorrow, first thing is you're doing mixer proportion, mixer design, right? Tomorrow morning, and then we'll do extrusion rheology. All right. So, Professor KVLS will do some more of rheology applied to your experimental measurements, and then we can go to the lab.
Thank you.